The last speaker this morning, Matteo Spadetto, and he will speak about strictifying path.
Thanks for this introduction, and let me thank the organizers, Lily, Thomas, Samuele, Pietro, and Cipriano for organizing this very nice event that I'm really enjoying so much. This is the workshop on doctrines and vibrations, so I thought that it is a nice occasion to talk a bit about the importance of the notion of relative vibrations in order to phrase and study the semantics of theories of dependent types. This is a joint work with Benno van den Berg and Daniel Otten, and it is about the problem of the coherence when we look for models of theories of dependent types. And I would like to start with this very famous example involving Sealy, about locally Cartesian closed categories. So categories with finite limits and such that any indexing functor, any pullback functor along a given arrow has a right adjoint. So the idea of Sealy was of considering these categories in the following way. We look at the objects of C as a semantic context, and we look at the arrows of target and object gamma as semantic types, capital A, in context gamma. And if we call such an arrow the type A, then we adopt this convention, this notation of denoting its domain in this way, gamma.A, because we think of the domain as the context extension of gamma via a variable of type A. Then the sections of a given display map, of a given arrow of the category, are the semantic terms of A in context gamma. So what Sealy showed in 1983 is that such a category can be seen as a non-genuine, this is very important, in a sense that we will recall in a bit, non-genuine model of a theory of dependent types with extensional inequalities, pulse and sigmas. Meaning that, apart from the problems that we are going to discuss, it comes with the right structure, the right property that allows you to deal with judgments involving these type constructors. For instance, let us talk for a minute about dependent sum types. You would like to validate the formation rule for sigma types. So what does it mean? That if you give me two type judgments, A in context gamma and B in context gamma A, okay, which means that you give me an arrow of codomain gamma for the first judgment and an arrow of codomain gamma dot A for the second judgment, then I should be able to give you back a new type judgment that I denoted this way, so the sigma type, which means that I need to give you back an arrow of codomain gamma. And I can pick just the composition of these two arrows, because essentially this means that I am post-composing by this arrow means to applying the left adjoint to the reindexing along this arrow, right? And this is essentially the reason why things work, because with this choice of the sigma type, you can see there's no need of going through details right now, but you can see that this validates, apart from the problems that we're going to discuss in a bit, it validates the introduction rule, the elimination and the computation rule of sigma types. Essentially, as I said, because you define the sigma type as a left adjoint to the reindexing along a given display map. The issues come when you would like to interpret the substitution. Suppose that you give me a type A in context gamma and a substitution for gamma, so a morphism of context F. Okay? Then I would like to validate for you the following type judgment, so that you have a type AF in context delta. And the natural choice, I forgot to say a thing that for today, for sake of simplicity, every wannabe model of a dependent type theory will be assumed to have a choice of reindexes. So for any arrow of C, in this case, I am already given a choice of a pullback along any given arrow F. Which means that if you give me a type A and a substitution F, then as a right candidate to validate this judgment, I can pick the reindexing of A along the F. Okay, and analogously for types, for sections. So if you give me a term A of type capital A, then I should validate for you the following judgment, which means that I should give you a section of the corresponding display map that we have just considered. And the right candidate is to take the unique section of this display map such that the following square commits. So we are using that this is a pullback. Anyways, this notion of substitution is a bit ambiguous in the following sense that there are several ways of seeing it. This is my favorite. That if you give me two substitutions, two morphisms of context, then you realize that there's a problem, because you would expect that if you substitute the composition, or if you just substitute twice, that you get the same object of the category. So that the category validates this judgmental equality between types or objects. But in fact, you only get a canonical isomorphism, because this is how pullbacks work. If you just give me a choice of pullbacks, there's no reason why the composition of a pullback, the composition of two pullbacks should be equal to the pullback of the composition. And analogously for sections, right? The two sections that you get by substituting the composition or substituting twice, they do not coincide. They just commute with this canonical isomorphism. So in this sense, C is not a genuine model of a dependent type, of some dependent type theory, because there's this issue with the substitution. You do not get validated these fundamental judgmental equalities. So one solution is to, by Curien, was to introduce explicit substitution on the syntax, or there's this other proposal by Hoffman, which is a coherence result for locally Cartesian closed categories, telling us that any locally Cartesian closed category is shown to be equivalent to a split. Split means that things work, that you do not have these problems with substitution anymore. Split comprehension category, still endowed with the right structure that allows you to deal with the judgments of extensional equalities, biases. So I remind you very briefly, a comprehension category is a Grothendieck vibration over the category of context, the category that you think of as the category of context, together with a fully faithful functor to the category of arrows that commutes with the codomain functor. This is not necessarily a vibration. And chi, the comprehension, is also required to preserve Cartesian morphisms. So sends Cartesian morphisms of P to pullback squares in C. You can still discuss dependent type theories in such a category, formally in the same way that we did for comprehension category. You have formally this for locally Cartesian closed categories. You have formally the same way of interpreting judgments. In particular, when such a comprehension category, P chi, is endowed with the right structure, the right choice of types in context to allow you to deal with extensional inequalities, bias, and sigmas. Anyways, this interpretation is still non-genuine in general, because if you just give me a vibration here, there's the same problem, right? Cartesian morphisms as abstractions of pullbacks of Cartesian squares carry on the same problem. They do not really agree with the composition, they just agree up to canonical isomorphism. And that is why I say that a split comprehension category is one where the given vibration is split. In this case, things work because the fact that the vibration is split forces in abstract, in E, a given type A to satisfy this equality, so that if I substitute twice, it's the same thing of substituting the composition. And then chi will take care of preserving this equality and making the pullbacks in C coherent. Hoffman's result tells us that any locally Cartesian closed category that can be naturally seen as a comprehension category is equivalent to such a split comprehension category with still able to interpret extensional inequalities, pies, and sigmas. And actually, this is a particular case of a bit more general result, which we might call right-adjoint coherence, because it is a co-free construction. If you consider the inclusion of a split comprehension categories into comprehension categories, this functor has a right adjoint that has this very interesting property. It sends any comprehension category into a split comprehension category, of course, because it needs to go in this direction, which happens to be equivalent to the comprehension category that you start from, equivalent in the category of comprehension, in the true category of comprehension categories. And moreover, this right adjoint has this property, that if you start from a comprehension category with extensional inequalities, pies and sigmas, and if these are pseudo-stable, which is a sort of pseudo-Beck-Chevalet condition, let us say, then this right adjoint preserves these constructors. Okay, so you move from a from a comprehension category with pseudo-stable type constructors to a fully split comprehension category with strictly stable type constructors. So you get a genuine model of a dependent type theory, a model where substitution works perfectly. This was done by Warren in 2008, and is based on the right splitting construction for rotating vibrations a la Benabou and Giraud. Now, this, let me just mention, and let me say that Hoffman's result is understood to be an instance of this theorem, of this coherence theorem. And we can do a similar thing for intentional identities. Because if you have, if now you consider, if you still consider the inclusion of split comprehension categories, this also happens to have a left adjoint, okay, which has the same property to send any comprehension category into a split one, which is equivalent to the one that you start from. And in this case, it works, in some sense, it works a bit better than the right adjoint, because you only require your type constructors to be weakly stable, which is way cheaper condition. Weakly stable just means, for instance, what does it mean that the sigma types are weakly stable? It means that if you reindex, the reindexing of a given sigma type is not required to agree in any sense with the sigma type of the reindexing. It's just required to being able to be endowed with a new structure of sigma type that nothing needs to do with the one of the choice. So it's a weaker condition, easier to find in nature. This was done by Lansley and Warren in 2015. Okay, so we have a coherence result for extensional identities. We have a coherence result for intensional identities. What about propositional identities? So I am interested in a weak notion of intensional ID types. So you know that you have an elimination rule if you're given a statement C dependent on an identity proof P, and if you're given a proof of that statement in case where you plug in a reflexivity, then you do have a proof of the general statement that here I call J. And the computation rule tells you that it coincides with Q in the hypothesis if you plug in a reflexivity as a identity proof. Well, I am interested in a weakening of this notion where in place of the judgmental equality, you just require an internal equality. You just require that there's a distinguished term in the corresponding ID type. These are called propositional identity types. They appeared in these two works, 2013, 2014, and this motivated Benno van den Berg to define his own notion of path category to have his own way of phrasing the semantics of these propositional identity types. Okay. I will not go through the axioms because this is a very short talk and no one wants to listen to a very long list of axioms, but let me just say that such a path category is a category with a distinguished family of fibrations, which will be the types in context. Actually, they are more the context in context, because in such a structure there's no distinction between types in context and context in context. And a class of weak equivalencies. They satisfy some properties. Maybe I will just mention, let us do that I just mention the properties that I need when I need them. Okay. Two classes of arrows satisfying some properties. Fibrations are in some sense the types in context, and weak equivalencies are the morphisms of context with a pseudo-inverse, so an inverse up to context propositional equality. Okay, so what's the point? If you give me a path category, then I can rephrase it for you as a comprehension category with particular properties. In the same way as you do for clans, for tribes, when you want to pass from clans to comprehension categories. You take as a domain of your fibration the display maps, that is the fibrations, the full subcategory of the arrows of C, whose objects are the fibrations, and this is clearly a Grothendieck fibration because fibrations are required to be closed under reindexing. Okay, and this clearly preserves Cartesian morphisms because it sends Kullbergs to Kullbergs, and it is fully faithful. So we get a comprehension category from a path category C. And how is characterized this comprehension category? Well, it has exactly propositional identity types, strong sigma types. Okay, let me comment this. Propositional identity types come because any diagonal factors as a weak equivalence followed by a fibration. And you pick the factoring object as the identity type or the identity context, because as I said, there's no distinction between context in context and types in context in this case. And the reason is because you have strong sigma types. Strong sigma types occur because you have fibrations closed under proposition, so you can define sigma types as we did for locally Cartesian closed category by post-composition, so left adjoint to the reindexing. And the third property is contextuality, which is equivalent to democracy in this case because you have strong sigma types. So contextuality means that any context of C is either the empty context or the extension, or the finite extension of the empty context via types. This is equivalent to democracy in this case, which means that any context is essentially a type in the empty context. And this is a consequence of the fact that the objects are finite, that any arrow to the terminal object is a fibration, meaning that any context can be seen as a type in the empty context. Yeah. Okay, so a path category is such a comprehension category with these properties, and vice versa. If you give me such a comprehension category with these properties, then I can use it to endow its base with a path category structure. Okay, so there's this mapping between path categories and comprehension categories with this property. I claim that this mapping form a biequivalence, but to be fair, I'm not completely sure. So for today, I'll just tell you that these two mappings agree with the equivalences. If you give me two equivalent path categories, then I can produce two equivalent comprehension categories with this property, and vice versa. Okay. Another thing that I'll tell you right now is that actually the propositional is that the path category gives you exactly that these propositional equalities and strong sigmas are weakly stable. So we are exactly in the condition to apply the left adjoint splitification and have everything preserved. But wait, we know for strong sigma types, we know for extensional inequalities, intensional inequalities, we still don't know for propositional inequalities. So what Benno, Vandenberg, Daniel Otten and I wanted to do in principle is to show that propositional inequalities are also get preserved by the left adjoint splitification. This is what we wanted to do. But luckily, Raphael Bocquet already did it. He already showed that propositional identity types get preserved by the left adjoint splitification. So thanks, Raphael, I do not have anything to do anymore, basically, because I just have to put together the results, because now we are done. Give me a path category C. We can rephrase it to a democratic comprehension category with weakly stable propositional inequalities and weakly stable strong sigma types in the way that I just told you. Now we apply the results by Lanze, Warren, and Bouquet to find an equivalent, to find a, just 1 minute and then I'm done, to find a, how's it called, a split replacement, so a democratic split comprehension category with stable propositional inequalities and stable strong sigma types, so a model where substitution works perfectly. Now we can apply the mapping back to rephrase this split comprehension category as a split path, a new split path categorical structure over the base C. And since the mapping preserves the equivalences, then the path category we started from is equivalent to the split one that we just got. So this is the result that any path category admits a split replacement is equivalent to a split path category. So we have a coherence result for propositional identity types. Now, if I can just have 1 minute more, 30 seconds, to say another thing that might be a bit more interesting is that this correspondence reminds me a bit about the one of Didier and Clérambault, where here in place of propositional inequalities you have extensional inequalities, and in place of path categories on the other side you have finite limit categories. In fact, finite limit categories are an instance of path categories, are precisely those path categories where the fibrations are, where all the arrows are fibrations and the weak equivalencies are the isomorphisms. So it would be nice to see whether this mapping generalizes the one by Didier and Clérambault. Now I'm done. This is what I wanted to say. Thank you for listening to this.
I wanted to tell that I did in my PhD thesis a correspondence between dependent theories and dependent theories of Lex category, regular category, arithmetic union, topos and toposes, and the corresponding structures by using exactly the right adjoint of the splitting fibration. So it works very well with the right adjoint. The only problem also with the right and the left is if you can internalize it inside the theory itself. Because usually they use higher order reasoning. You need a universe on one side and split fibration which are not small. But I did the same before, what's the name? BBR, and simply that I used a different notion of morphism between theories because I was stick to the theoretic notion of translation.
Right.
But it can be done.
So you consider strong functors that strictly preserve the context extension?
Because this is my way to go from categories to dependent theories back and forth for all the structure that toposes, regular categories, arithmetic universe, everywhere. If they are extensional, of course, based on finite limits.
Mm-hmm.
So that's what
I see. Thank you.
Another question. Are the identity types in the left adjoint splitting still propositional, or do you have a definitional computation rule?
No, they remain after applying the left adjoint, they remain propositional, but they get strictly stable under substitution. But they remain propositional, yes.
Matteo, a slightly different sort of question. When you started, you talking about series non-German models and said that there was a Hoffman solution and a Korean solution. And if I remember correctly, there was a later paper which actually put the two together. Have you seen that?
Yes, the one with Richard Gardner. Yeah.
Exactly. So what I kind of wanted to ask you is whether, and I wanted the solution of Korean because of the explicit substitutions. So I was wondering whether the stuff that you're doing now can be pulled back to explicit substitutions or not.
That would be very nice to see, but I guess so. Yeah, I guess one can adapt.
Strictness, so we organize that we need a specific.
Do you think it's doable, really?
Huh?
Do you think it's doable?
No, and you don't need a explicit substitution because you have erased the problem. But I want to have the explicit.
Sure.
Yes,
Because everything is propositional, so it's
but if you have an active theorist, I want to go back to the usual. Yes, okay, thank you.
Other questions? No?